Precalculus, Chapter 2A, Day 1. Let's look at these notes. We're going to be working with polynomial functions. Now, you've used the term polynomial in the past. Polynomial has, the prefix poly in it, which means multiple, and then nomial is indicating terms. So if we have multiple terms, okay, we have a polynomial. So we look at an equation of a polynomial function, and we say we can have a coefficient, which is just the number in front of the letter, and then we can have a variable raised to a power, okay, or multiple variables raised to the powers. Right? Now it says n is the degree of the polynomial, must be a whole number. Now notice that n is the highest exponent of the variable. All right, so this is the highest exponent of a variable. A sub n is the leading coefficient. Now, A sub n, this is kind of important. A sub n goes with the variable that has the highest exponent. So even if this term were second, third, fourth, fifth, even last being listed in the polynomial, that is still the one term out of the entire polynomial that you're going to look at for the degree and the leading coefficient. Okay, so the coefficient of the variable that has the highest exponent, not necessarily the coefficient that comes first, not necessarily the variable that comes first, but the one with the highest exponent, that is the term that's going to determine what our degree and leading coefficient are. So let's look at the first example that they give us here. They give us this lovely f of x polynomial, this function. So 2x to the fifth plus 3x to the fourth minus x cubed plus 4x squared minus x plus 5. And they've done a nice job at giving us a nice, neat, descending ordered polynomial. You start with the fifth degree, then the fourth degree, then the third degree. Okay, they didn't try doing anything tricky. Okay, so what is the highest degree or the highest exponent of a variable? Well, it's this 5 right here. So this is a fifth degree polynomial. Now, because it's a fifth degree polynomial, we're also going to use that coefficient to answer the question, what is the leading coefficient? So the leading coefficient is 2. It's that simple. Right? Now, if that 2x to the fifth were at the end of the polynomial, the answer would be the same. Right? The answer would be identical. So don't let the fact that this particular example lists it first confuse you. The highest exponent of a variable tells you the degree, and that term's coefficient is the leading coefficient. All right, so something about graphs of polynomials. They are continuous, which I like to say if you start on the left and you go all the way to the right, that you never have to pick up your pencil or marker or whatever these things are here, styluses or, yeah, whatever they are, it's continuous. Okay, there are no gaps in your domain. Okay, once you start, you keep going. Okay, and there are smooth, rounded turns. You say, well, what's not a smooth, rounded turn? Well, if you remember absolute values in the shape of a V, that right there, the vertex, is not a smooth, rounded turn. Okay, that is a sharp, non-rounded turn. Therefore, that is not a polynomial. Polynomial must be described as a set of terms that has coefficients and then x to a whole number power, okay, or some variable to a whole number power. An absolute value is not a whole number power. Okay, so let's go down the page a little bit. All right, so now, if n is odd, okay, so that means the exponent, okay, so that's the exponent. The exponent is odd, and a sub n, which is the leading coefficient is positive. What does that generally look like? Well, I like to think of the easiest odd number that I can have come to mind, which is 1. So y equals x to the first tells me that I have a positive 1 as my coefficient, and x to the first tells me that my exponent is a positive 1. 1 is odd. So what does y equals x look like? This is what y equals x looks like. X to the first looks like this. All right. So what they want you to think about is this: the end behavior. Okay, the end behavior. As x approaches infinity, okay, as we go to the right, as this graph goes further to the right, what does y do? And you can see that it's going up. Okay, it's going up as we go to the right. So this thing right here, this is read the limit of f of x, or the limit of y, as x approaches infinity. So as x goes to the right, to the end of your graph, okay, as it goes forever to the right, where is your y, or your f of x, going? It's going up. So it's going to infinity. Okay, that's going up to the right. Now, what if we have x going towards negative infinity, which just means we're going to the left. So as x goes to the left further and further toward the end of your graph, what is y doing? Okay, so the limit of f of x, or where is y going when x approaches negative infinity? Well, this one's going down. So downward approaches negative infinity. Okay, so what are you remembering from this? When your exponent, or your degree, is odd and your coefficient is positive, then you're going to have what we call a down-up graph. Means to the left it goes down when you go to the end of the graph. To the right it goes up as we go to the right end of the graph. Okay, so it starts down, it goes up. Okay, next one. If your degree is odd again, but this time you have a negative coefficient in your leading term. So y equals negative x to the first. Right? And I understand it should go through the origin, but I'm just looking at end behavior. So this is the direction that negative x to the first would take you. Okay. The 1 is odd. The negative 1 as the coefficient is negative. Cool. So the limit of f of x, or where is y going, as x approaches infinity. So as we go to the right, where is my graph approaching as far as the y value? It's going down. So this time, to the right, it's going to negative infinity. The limit of f of x, or where is y going, as x approaches negative infinity. So as x goes to the left, near the end of your graph, this one's going up. Well, up indicates that my limit is positive, or regular, infinity. Okay? So if you have odd degree polynomial, negative leading coefficient, then you have, from left to right, what we call an up-down graph. Okay, it starts up at infinity and it ends going down to negative infinity. Okay, what happens in between, we don't know. This is just the end behavior. This is how it behaves at the left end and the right end. Okay, so now let's go to a different one. Let's say that n is even. Okay, so an even degree. Okay, the exponent of your leading term is even, and your leading coefficient is positive. So an example of that is positive 1x to the, think of an even number, nice and easy, x squared. Okay, what does x squared look like? Well, it looks like those lovely parabolas that you've been working with since Algebra 2. So let's examine this, shall we? So the limit of f of x, or where is y going, when x approaches infinity. So as we go to the right, as this graph is going to the right, where is your f of x going towards? Where is your f of x approaching? Where is y approaching? Well, it's going up. So if it's going up, it's approaching infinity. As x approaches negative infinity, what is your limit of f of x? Or where is y going? Well, to the left, it's still going up. So as I go to the left end, it's up. If I go to the right end, it's up. So infinity is the limit on both sides. And that tells me that if I have an even degree polynomial with a positive coefficient, that I'm going to have an up graph. Because to the left, the end behavior says it's going up. And to the right, the end behavior says it's going up to infinity both ways. Right? So the last one, what if it's an even degree polynomial, but a negative coefficient, leading coefficient, right? Well, how about negative x squared? It's negative, right? So negative x squared. Well, negative x squared looks like one of these. Again, I know it should touch the origin, but I'm looking at end behavior, so I'm not terribly worried about my sketch. Okay, so where is y going, or the limit of f of x, as x approaches infinity? Okay, the limit of f of x as x approaches, so as x goes to the right, this graph is going down. The function is going down. The y values are going down. So it's approaching negative infinity. As it goes to the left, or towards negative infinity, the limit of f of x, or where is y going, is again negative infinity. So if I have an even degree polynomial with a negative leading coefficient, I'm going to have a down graph. Okay, both ends, left and right, that graph is going towards negative infinity. So let's apply that here. This should be two of the easier questions we have for any unit, right? Question number 1. Right? Let's describe the end behavior using limits. So we are going to say the limit of f of x, or where is y going, as x approaches, and let's start with negative infinity. As x approaches negative infinity. Okay, well, look at this polynomial, and we say this polynomial has what degree? Well, let's see. My exponents are x to the 0 here, which 0 is not going to be the highest degree, hopefully. And we got a 3, and we got a 5. So that tells me this is a 5th degree, which means it's an odd degree. And the leading coefficient is a positive 4. So positive leading coefficient, that's my LC. So it's 5th degree, positive leading coefficient. So odd positive coefficient. That tells me it's a down up. So down to the left. So as we go towards negative infinity, the y, or f of x, values approach negative infinity. And then the limit of our y's, or limit of f of x, as x goes to the right, so x goes to infinity, that limit is, well, it's a down up. So it's going up to infinity. Right? Let's look at example 2. Okay, this is a 6th degree, okay, because 6 is the highest exponent of a variable here. 6th degree, and the leading coefficient is a negative 2. So negative leading coefficient. So it's an even degree, negative leading coefficient. Okay, so think of x squared with a negative in front of it. It's going to be going down, down. Okay, so that makes it kind of easy on us. Let's pick the limit of f of x as x approaches negative infinity. So at the left end, okay, the limit is negative infinity. How do I know? Because if it's negative leading coefficient and it's an even polynomial, it's going down both ways. Cha-ching, cha-ching, okay? Down to the left, down to the right. And then likewise, the limit of f of x as x approaches infinity, okay? We said it's a down, down, so again, it's going towards negative infinity. Okay, let's proceed. Zeros and turning points. Okay, now we did zeros in chapter 1. Right? Remember, zeros are x-intercepts. Right? You already have that. You already know that. Okay, so we're looking at our zeros. Okay, so like here we got, I can see 3 different zeros because the x-intercepts are pretty obvious. They're there and there. Okay. The second graph, I can see 1 x-intercept. Here I can see a couple. All right. And this one's got a bunch of them. 2, 3. I can see 4 of them on that one. So there's a bunch of zeros, a bunch of x-intercepts. Turning points. Turning points are local or relative max and mins. Okay, local extrema. So if you have in this case a local max, that's a turning point. Okay, that's a turning point in your graph. A local min or an absolute min is a turning point. Okay, so any min or max, every extrema, is going to be a turning point for you. All right, so let's see. Cubic functions. Okay, here are some cubic functions, typical cubic functions. Make this real simple. Cubic, 3rd degree, have at most 3 zeros. That's it, done. Cubic functions and turning points. All you need to know for the turning points. Okay, by the way, how many turning points does this guy have? Hopefully you can say, well, there's a max and there's a min. There are local max and mins. There's 2 turning points there. This cubic function doesn't look like it has any. Okay, cubic functions have at most 2 turning points. Right? All you do is you subtract 1 every time from the maximum number of zeros to get the maximum number of turning points. Okay, you'll see that in a second. So quartic functions, fourth degree functions. So here are quartic functions, all graphed out nice and beautiful for you. So remember, here's one that has 4 zeros. Right? Here's one that only has a couple zeros. Okay, quartic functions, because it's a fourth degree, have at most 4 zeros. Easy. So we just said, if I want to know how many turning points they possibly could have, the maximum number of turning points, well, you take the degree and you subtract 1. So 4 minus 1 is 3. Okay, now they're just going to say, okay, what's the pattern? The pattern is, if the degree is n, then they have at most n zeros. So if it's a 72nd degree polynomial, there are at most 72 zeros. And then they would have at most n minus 1 turning points. So a 72nd degree polynomial could have up to 71 turning points. I won't ask you to graph that. I don't want to graph that. My calculator doesn't want to graph that. Okay, let's continue. More information about zeros. If f is a polynomial function and c is an x-intercept, okay, c is a 0. Okay, we already said x-intercepts are zeros. X equals c is a solution to your equation. Okay, if I say, what is x to get y to be 0? Okay, when I solve it, x equals that number. That's a solution, okay? Any 0, x minus that number is going to be a factor in your equation, okay? It's going to be a factor in your equation. So let's look at this real quickly. So I've taken the liberty of graphing x squared minus 3x plus 2, which is the example given here in this box. And it says 1 and 2 are x-intercepts on the graph. Well, take a look. Here they are. There's 1 and 2 as your x-intercepts. And that's lovely. Okay? 1 and 2 are therefore zeros of your function. Now, I want you to look on the right side here. It says x minus 2 and x minus 1 are factors. So I just want to do one thing here. Check this out. I'm going to go in and I'm going to say x minus 1 times x minus 2. Now, is it the exact same graph? Yes, it is. It's identical. Okay? Because what did we just do? We took x squared minus 3x plus 2, and we did the product sum, and we found the factors. Okay? So when we solved this for equals 0, we found that 1 and 2 are solutions. So you go x minus 1 and x minus 2 are factors. So here are the factors of this quadratic. Okay, that's all I wanted to do on that. We'll go back to our note sheet now. So back to our note sheet. So this little part here just simply says that if we take our solutions and we substitute them for x, that we do get 0. Okay, that's why we call them zeros of the function. All right, so let's do example B. First, we're going to say how many possible real zeros are there and how many possible turning points there are. Then we're going to determine the zeros by factoring. Now, can we check this by graphing it? Yes, but we're not going to do it by graphing. Okay, your grapher is your validation, your checker, right? So let's say possible real zeros. So how many possible real zeros are there? Easy question. What's the degree of your polynomial? Okay, well, the highest exponent on an x that I see is 3. So it's a third degree polynomial, so there are 3 possible real zeros. How many possible turning points? I'm going to put TP. Get your laughter out of the way if you want to. Middle school just called. They want their ha-has back. All right. Okay. Possible turning points. You just subtract 1 from the 3 and you get 2. So x cubed minus 6x squared minus 27x has at most 3 real zeros, has at most 2 turning points. All right, now it says let's determine the zeros by factoring. Well, I would do the product sum, except that they all have a GCF, and I want to factor out my GCF first. So let's see, the coefficients are 1, 6, and 27. Yeah, I'm not going to have anything divide out of that, but they all have an x. So let's factor out an x. So divide x cubed by x, get x squared. Divide minus 6x squared by x, get minus 6x. Divide negative 27x by x, and you get minus 27. Right? So we're going to keep this x, because that's going to be one of our zeros here coming up that we're going to need for a solution. And now we're going to factor. Okay, product sum. Product sum, if you want to make the little chart. Okay, the product has to be negative 27, and the sum has to be negative 6. So what two numbers multiply to give you negative 27 that add to negative 6? Well, I'm pretty sure it's going to be negative 9 and positive 3. They add together to give you negative 6, and the product is negative 27. So we got x minus 9, x plus 3. Okay. So now, because we want to know if these are zeros or not, we're going to say, when does this equal 0? Well, we've got this times this times this equals 0. So any of those will give you one of your zeros. So let's find a solution. Solution, x equals 0. Next solution. Okay, if x minus 9 equals 0, you add 9 to both sides, okay? And you get x equals 9. X plus 3 equals 0. Subtract 3 from both sides. X equals negative 3. Okay, so we have determined all 3 zeros, all 3 solutions by factoring. And if you put this polynomial in your calculator and you look at your x-axis, you will see that the 3 intercepts are negative 3, 0, and 9. Go ahead and check it on your own time. Let's do question 2. Okay, I'm going to do a little erasing here. All right, question 2. First off, how many possible real zeros are there? Well, it's a 4th degree polynomial, so 4 possible real zeros, which tells me that there are 3 possible turning points. Great. Now we want to find out what those zeros are, finding the solutions by factoring. So we've got x to the 4th minus 9x squared plus 16. Are there any GCFs? Nope. Okay, because this term doesn't have any x's in it, and this term has a coefficient of 1, so there definitely isn't a GCF that we're going to be dividing out. So guess what we're going to do? We're going to see, because they told us to factor, we're going to go straight to product sum. Okay, so what times itself gives you x to the 4th? Well, that's x squared times x squared. Now product sum. Product is going to be positive 18. Sum has to be negative 9. Okay, so what two numbers multiply to give you 18 that add to negative 9? Think we would be in good shape with negative 6 and negative 3. They multiply to positive 18, and their sum is negative 9. So product sum, it's all good. All right, so minus 6, minus 3. Minus 6, minus 3. All right, so we can split this up, and we could say that x squared minus 6 could equal 0. Also, x squared minus 3 could equal 0. So how do we solve this? Well, I would add 6 to both sides here. I get x squared equals 6. We don't want to have squared, so let's square root both sides. Every time that you square root both sides, you have to have a plus minus in your answer. So x equals plus or minus root 6. So positive root 6 is a 0, negative root 6 is a 0. Okay, let's do the same thing on this side. X squared minus 3 is going to equal 0. So I'm going to add 3 to both sides. Get x squared equals 3. Okay, I did plus 3 plus 3. I just didn't write it down. Now I'm going to take the square root, both sides. When you square root both sides, you must remember to plus minus your answer when you square root both sides. So how many real zeros are there? Well, here's 2. Positive root 6, negative root 6, and here's 2. Positive root 3, negative root 3. There's 4 of them. Oh, look, that is the maximum number of real zeros that we've said that could have. So I would say, go ahead, put that in your grapher, take a look at it, and see if positive, negative root 3 and root 6 are actually the zeros there. Okay. Moving along here. We got this pretty function right here. Okay. So just to reemphasize what we've looked at, we talked about if C is a 0, then x minus C is a factor. Okay, so look at these factors. Okay, so the x minus 3, what does that tell me? This guy right here tells me that 3 is a 0. And look at the graph. There's 3, and it is a 0. Look at this x plus 2 squared. And x plus 2 is like x minus negative 2. So that tells me that negative 2 is a 0. And there it is, right there. Okay. And then finally, there's an x minus 1 cubed. Okay, that's a fact. So x minus 1 tells me, that 1 is a 0. And right there, 1 is a 0. Okay, so that's just a little tying in everything that we just did. You have solutions, which are zeros or x-intercepts, and then x minus any of those x-intercepts is a factor of the equation itself. Okay. Home stretch. Possible real zeros, possible turning points, and then factor to determine all of the real zeros. So first thing, we're going to look at this polynomial and say that 4 is the highest exponent. So there are a possible, I'll put possible, and I don't want anybody to think I wrote positive. Okay, possible real zeros would be 4. And possible turning points could be 3. Okay, so now it says, let's factor these little sweethearts. Is there a GCF? Yeah, they all have x squared in them. So let's factor x squared out. So x to the 4th divided by x squared is x squared. Plus 5x cubed divided by x squared is plus 5x. and then plus 6x squared divided by x squared is just 6. Okay, now we're finding the zeros, so let's set it equal to 0. That's a 0, trust me. Okay, so we know we're going to end up with the x squared equals 0 as part of our solution, but let's factor x squared plus 5x plus 6. Okay, so product sum. Product sum. Product is positive 6. Sum is positive 5. Okay. Just remember, 1 and 6 do not add up to 5. Okay, so don't say this is 1 and 6. This is going to have to be positive 2 and positive 3. 2 times 3 is 6. Positive 2 plus positive 3 gives you positive 5. Okay, so we're going to have a plus 2, or x plus 2, and then x plus 3. Okay, so we're going to split these little things up. You've got x squared equals 0. Take the square root of both sides. Now, granted, I said whenever you take the square root of both sides, you go plus minus, but plus minus 0 is 0 twice. So x equals 0. X plus 2 equals 0. Subtract 2, you get x equals negative 2. X plus 3 equals 0. Subtract 3, you get negative 3. Okay, so those are your real zeros. Now, at most, we could have had 4. We got 3. Okay, you don't have to have 4 every time. 4 is the number of possible real zeros. It's not the number that you have to have of real zeros. You might have a quartic with 0 real zeros sometime, okay, that never touches the x-axis. Okay, look at question 2 here. Question 2, we got 3x to the 5th minus 18x to the 4th plus 27x cubed. Okay, that's pretty. What is the GCF? We start right off with our GCF. Well, they all have at least x to the 3rd, so they all have x cubed. 3, 18, 27. 3 is a factor of all of them. So I'm going to say 3x cubed is what I'm going to factor out. Okay, so if I divide 3x to the 5th by 3x cubed, I get x squared. Minus 18x to the 4th, well, divide that by 3x cubed, I get minus 6x. And then 27x cubed divided by 3x cubed is positive 9. Okay. All right. Now, those of you that are saying, hey, wait, we didn't say possible real zeros and turning points. Good, let's do that. So, possible real zeros. How many possible real zeros? Well, it's a 5th degree polynomial, so 5 equals 5. It's an equal sign. It's not negative. I don't want to make it look negative. It's 5 equals 5. There we go. Okay. Possible turning points. It's going to be 5 minus 1, 4. Every time. Okay, here we go. We make this equal 0. We're going to find the zeros by factoring. So we've already factored out the 3x cubed. Okay, now some product sum. The product is going to be positive 9. Oh, yeah, positive 9. You can put it in here. And the sum is going to be negative 6. All right, so what times what gives you positive 9 but adds to negative 6? I think this one's pretty straightforward. I think it's negative 3 times negative 3 gives you positive 9, and they add to negative 6. So I got x minus 3, x minus 3. Okay. So now that we just have product, 3x cubed times the parentheses equals 0. We can split it. So we got 3x cubed equals 0. You could divide both sides by 3. You get x cubed equals 0. You take the cube root of 0, and you get 0. X minus 3 equals 0. Add 3 to both sides. You get x equals 3. And you get x equals 3 again. So 3 and 0 are your two real zeros of this 5th degree polynomial. Now, we could have had up to 5. Okay, we could have had up to 5. We got 2. That's okay. All right. So now let's look at our last question here. Example D. Given f of x equals negative x times x plus 3 squared times x minus 5. State the end behavior of the graph. Determine the number of zeros. State the multiplicity of each 0. Then graph the function. Now we're going to have some fun. This is going to be where we are the calculator. All right. So check this out. Let's do the end behavior first. End behavior. Remember, we can tell the end behavior. Let's write this over here. End behavior. Okay. The end behavior is going to be determined by the degree of the polynomial and the leading coefficient. All right. So the degree of the polynomial. Now, you don't need to multiply this whole thing out. If you need to, for your sake, go for it. But you don't need to do it in order to figure out the end behavior. So what is the degree of the polynomial? Well, if I have x to the first and I have x squared and I have another x to the first, I know that I'm multiplying x times x squared times x. And when you multiply the same bases, you just add the exponents. So x to the first times x to the second, 1 plus 2 is 3, times x to the first, 3 plus 1 is 4. So when I multiply this all out, my highest degree, my highest exponent is going to be x to the 4th. So it's a 4th degree. Okay. So because it's 4th degree, which is even. Okay. Remember evens? Let's go back. The even ones either go up, up, or down, down. Okay. The even ones either go up, up, or down, down. The only thing you need to look at is that leading coefficient. So leading coefficient, let's see what it is. Just take the coefficients here of x. -1, so you got -1. And then what's the coefficient of x here? It's 1, and it's squared. And then this one is 1, okay? And you multiply it. That will be your leading coefficient at the end, okay? So -1 times 1 squared is 1 times 1. So -1 times 1 times 1 is -1. So we have a 4th degree polynomial with a negative leading coefficient, okay? I recommend you go back and rewind that little part and follow what I just said there, okay? So it's even. And the negative coefficient tells me that it's going to be a down, down. Down, down. So that means I'm going to start down and I'm going to finish down. Okay. So step 1 I did in gray. Okay. The end behavior of the graph tells me I'm going down, down to the ends. Now what's in between? Okay. The number of zeros, the multiplicity of each, which we're going to get to, which is fun, and then we're going to graph it freehand. Okay. Now our zeros. This one is this question is actually easier than what we just did because they've already done all the factoring. Right. So where are my zeros? Well, we know that -x could be 0. We know that x plus 3 could be 0. We know that x minus 5 could be 0, okay? -x, x plus 3, x minus 5, okay? And you say, well, what about the exponents? If you go x plus 3 squared, equals 0, you're just going to say, I'm going to take the square root, and it's square root of 0, so you're going to go right back to that. X plus 3 is going to be 0. So negative x equals 0, divide by negative 1. X plus 3 equals 0, subtract 3. X minus 5 equals 0, add 5. So we're going to take those 3 points, and we're going to show that they're zeros by putting dots on 0, negative 3, and 5. So I know right now that it's a down, down at the end. And in the middle here, we've got 3 x-intercepts. So now, is it going to be like this, then down? Is it going to be like, it's going to be like that, okay? Well, that's when we're going to talk about the multiplicities of the zeros. This is cool. Okay, multiplicities. Because this was x to the first power, the multiplicity at 0 is 1. When the multiplicity is 1, we cross the x-axis. Okay, we cross the x-axis. So wherever you hit this one, it's going to go straight through it. Okay? For x equals negative 3, it was to the second power. Okay? That means the multiplicity is 2, because it's x plus 3 times x plus 3. There's 2 of them. When the multiplicity is 2, we bounce off the x-axis. Okay? Pre-calc books that I've taught out of in the past have actually used the term kiss the x-axis. I like bounce. Hopefully you like bounce. Okay, so let's bounce. All right. So that means when it gets towards that negative 3, okay, it's not going to cross it. It's going to bounce off of it. Boom. Right? And then what about the 5? Right? The 5, it's a multiplicity again of 1. So multiplicity of 1. And so it's going to cross the x-axis. Okay, so these are the things we need to know. Now we can do all the freestyle, by hand graphing, right? And then you can check it with your calculator. I know I'm starting down. When I get to the negative 3, according to my multiplicities, I'm going to bounce off of the x-axis, okay? So that's the first thing. I'm going to start from down. I'll move my arrow over just a little teeny bit, okay? So from down. So I'm going to come up and I'm going to bounce off of negative 3. Okay? So I'm bouncing off of negative 3. Done. Now I know that I'm going towards 0. And at 0, my multiplicity was 1. I'm going to cross the axis. Okay, so I'm going to bounce here. I'm going to cross the axis. Okay? And now I'm going to get to the 5. And the 5 says I'm going to cross the axis again. Which is good because now I know I have to finish going down. So if this had said bounce and we did this, I go, uh-oh, that's a red flag because I can't end going down if I bounced there because I don't have any more x-intercepts. I don't have any more zeros. So after you finish the last 0, you better be going in the direction you're supposed to be going, right? So I'll move the arrow here just a little bit and Right, and there's a good freehand representation of the graph. I recommend that you go ahead and you put that in your calculator. The only thing that the calculator will show you is, how far does this dip? How high does that peak? And it'll give you specific points, but this point and this point and this point, they all have to look like that, right? The only thing that we did not cover today here is the exponent or the multiplicity of 3, right? And I'm just gonna show you very quickly. Let's say that we had x cubed. Remember x cubed, y equals x cubed, or f of x equals x cubed, all right? Remember what that looked like? It looked like this. That's what y equals x cubed looked like. So right here, you could say my 0 is obviously 0, right there. Okay, so with that in mind, I'm asking you, what happens here at that 0? At that 0 of 0, it crosses, okay? So with a multiplicity of 3, what happens? It crosses the x-axis, but notice it doesn't just cross it or even cross it. It doesn't cross it and just keep doing the same thing. It's like, okay, I'm concave down, okay? I'm shaded down here. And now as I touch it, I'm concave up, okay? It's a turning point. It's not, well, it's an inflection point. It's not a turning point, okay? Not a turning point. It's an inflection point, right? So what happens is it crosses and it flattens, okay? So if I have something cubed, like if I have, x plus 7 cubed in my answer, that means at -7, when it crosses, it's going to flatten as it crosses, just like y equals x cubed flattens as it crosses the origin. Okay, all right, that's it for day 1. Looking forward to day 2. Hopefully you enjoyed this one. There's a lot of stuff in here, so go back, rewind it. Not difficult concepts. Just make sure that you don't skip anything. Okay, do the practice that's right after this on your worksheet. Okay, see ya.